My name is Joseph DeGaulle, and I'm going to be presenting my paper with Mani Golparvar-Fard and Derek Hoyme, titled Geometry-Informed Material Recognition. So we address the problem of recognizing materials in real-world scenes given images and sparse geometry. So for example, I've highlighted brick, concrete, foliage, and metal in both the images and geometry of this slide. So we make two contributions. The first contribution is a data set, which is split into two parts. The focus scale part consists of 19 material categories. So for each material category, there are multiple surfaces per category. So for example, brick, I'm expanding brick to show many different surfaces. For each of those surfaces then, we collect 8 to 12 images at different perspectives. We use those images then to do 3D reconstruction, and we also extract image patches, and then we pair the geometry with the image patches. The other component of our data set is scene scale. So in this case we have 160 images of a construction site, and then we have the corresponding 3D reconstruction from those images. So that's 160 calibrated cameras and over 900,000 labeled 3D points. So the second contribution that we make is that we investigate how to use 3D geometry to aid material recognition. So the first approach that we tried is what we're calling independent modeling, so basically using the normal vectors, clustering building histograms. The second approach is to take image features, so this could be Fisher vectors, convolutional neural networks, and we concatenate the normal vectors onto those features and then do our modeling. This is what we call joint modeling. Then the third approach is to use the camera calibration information to do a frontal rectification prior to feature extraction. So for results, I first wanted to show a qualitative result that really demonstrates the power of the 3D approach. So what you're seeing here is paving and stone limestone. These were two often confused categories using a state-of-the-art 2D approach, but with using 3D information we were able to mitigate this confusion. So I think it's obvious in the 2D case, you can see that paving and stone limestone are both gray, they're both blocky, they both have mortar, and then you can see how using the 3D surfaces it becomes much more differentiable. So then some quantitative results I wanted to highlight. First, FV plus CNN is a state-of-the-art 2D approach for material recognition. That's Fisher vectors plus convolutional neural networks. And then using the -n we denote our joint approach, and I'm highlighting in orange a gain of about 5%. Highlighting in pink a gain of about 3%. Then looking at just the best 2D approach, which I have in purple, versus the best 3D approach, which is in yellow, you see a gain of about 5%. And then also that the geometry improves the classification accuracy across viewing directions and scales. So this plot that I have here is showing the accuracy across scales, where the purple bar is the best 2D approach and the yellow bar is the best 3D approach. So you can see that the yellow bar improves for all 4 scales. So that's it. Thank you for listening.